Hey again, this is Matt. In today's video, we'll look at an introduction to trigonometry. Specifically, we'll look at right triangles and their relation to the unit circle. The ancient Greeks developed trigonometry, which literally means the measure of angles. They created trigonometric functions such as sine, cosine, tangent, cotangent, secant, and cosecant, and defined them as the right triangle ratios of side lengths. They used this in order to calculate the size of the Earth, to study astronomy, and many other applications in mathematics. To do this, they looked at specific triangles to start with. One of those is the 45-45 isosceles right triangle. Isosceles because the two side lengths are equal, and it forms a 90-degree angle for the hypotenuse, which is length 1 we'll define. So if I define the hypotenuse to be length 1 and I have unknown side lengths, I can use the Pythagorean theorem to solve. I group my like terms together, I isolate x by itself, I take the square root, and I solve for those side lengths. So now that's the square root of 2 over 2. So now I have a triangle whose angles and side lengths I know. Another special triangle is the 30, 60, 90 degree triangle. We get this by taking an equilateral triangle of having side lengths of 1, all of equal length. And if I imagine cutting this triangle in half, then I've bisected the 60-degree angle to create a 30-degree angle. I could think of this triangle by itself, and now I have a hypotenuse of 1, one side length of a half, and an unknown length x. Again, I'll use the Pythagorean theorem to solve for x, isolating x by itself, taking the square root, and I get a side length of the square root of 3 over 2. So I could do this for any triangle. So I could conceive of theta as being an acute triangle, meaning it's less than 90, and I could think of a triangle having theta as its angle, and it'll have a side of A, B, and a hypotenuse of C. So given A, B, and C, there are 6 different ratios that could be defined. B over C, A over C, B over A. And these ratios then are assigned the trigonometric function. So we've basically taken the 6 possible combinations of side lengths and we code them to trigonometric functions. So for instance, sine of theta is B over C, cosine of theta is A over C, and tangent of theta is B over A. Now, an alternative form for the trig equations, instead of conceiving them as A, B, and C, which are arbitrary, we can instead relabel our triangle with adjacent, as it's the side length that's adjacent to theta, opposite, as it's opposite of theta, and the hypotenuse. If we do this, then our trig function sine becomes opposite over hypotenuse, cosine becomes adjacent over hypotenuse, and tangent is opposite over adjacent. Likewise, cosecant, secant, and cotangent are still considered the reciprocals. Now, people will often try to remember this with the acrostic sa, ka, toa. Sa, or SOH, meaning sine is opposite over hypotenuse. Ka, which means cosine, is adjacent over hypotenuse. And toa, TOA, as tangent is opposite over adjacent. So we'll go back to our triangles. We can actually calculate now the trigonometric values for our given angles. So for 45 degrees, sine being opposite over hypotenuse is square root of 2 over 2, all over 1. So the sine of 45 degrees is the square root of 2 over 2. Cosine, which is adjacent over hypotenuse, square root of 2 over 1, which equals the square root of 2. And tangent is equal to 1, which makes sense because it's the ratio of those two side lengths, which they're equal, so the ratio is 1. I can do the same thing for the trigonometric values for 60 degrees. 60 degrees, so sine being opposite over hypotenuse, square root of 3 over 2 over 1. Cosine, 60 degrees, which is adjacent over hypotenuse, which is a half. And the tangent, square root of 3 over 2 all over 1 half, we can simplify that to be square root of 3. I'll do the same thing for now the trigonometric values for 30 degrees. I have my triangle, I look at the 30 degree, sine of theta for 30 degrees is a half, cosine is square root of 3 over 2, and the tangent, being opposite over adjacent, is a half over the square root of 3 over 2, which simplifies into 1 over the square root of 3, And if I rationalize that, meaning I put the radical in the numerator, I turn square root of 3 over 3 as the tangent value. Now that I have all these trigonometric values and triangles, what I can do is I can organize them on the Cartesian plane in a way that adds additional properties to my trigonometric functions. So for instance, I can conceive of taking the 30, 60, 90 degree triangle and aligning it on the Cartesian plane around the origin. So you'll see here then that angle that it makes here between the positive x-axis and the triangle is 30 degrees. And so this coordinate point here is square root of 3 over 2, comma, 1/2, because the x length here is square root of 3 over 2, and the height, which is the y length, is 1/2. And the hypotenuse here is 1. So I could lay that triangle down there, and I could conceive of doing this now with my 45, 90 triangle. I could think about creating the 60 degree triangle with the 60 degree angle from the positive x-axis here. And then again, this point here now would be 1/2 square root of 3 over 2. And I could do this then in the second quadrant. So I can conceive of now taking these triangles and putting them here. I could do them in the third quadrant and the fourth quadrant, and because these all have hypotenuse 1, each of these coordinate points lies on the circle centered at the origin, or the unit circle, because it has radius 1. So we'll see that here. So each of those triangles now lies on the unit circle with one of those points. And I could think then of looking at all of these values, all of these triangles. And this is fairly common. This is the unit circle. This is what we know, and this is a unit circle in which we want to memorize. And the reason we do this is because it gives us additional information. So if I think of, well, the 30 degrees, the angle here is 30 degrees. So the x-coordinate, square root of 3 over 2, well, that's going to have the same as the cosine of 330 degrees, because it's the square root of 3 over 2. But the y values, so the sine of 30 degrees being 1/2, the sine of 330 degrees will be negative 1/2. So I can use information about which quadrant these angles lie on to determine whether they're positive or negative. In addition, because each of these points, x comma y, is cosine theta, sine theta, I can derive my first trig identity. So x squared plus y squared equaling r squared, an equation for the circle. That means cosine squared plus sine squared will equal 1. Oftentimes, though, trigonometric functions are defined in terms of radians and not degrees. Now, all radians are is a relation between the arc length and the radius of the circle that we're dealing with. So if we're dealing with the unit circle, so if this length was radius 1, then 360 degrees, a full revolution, would be the circumference of the triangle. So 360 degrees would be the same as 2 pi. So that means 180 degrees would be pi, and I could continue to take this ratio in order to figure out, well, what is the radian measure? And I could do this for any length or any radius or size circle that I have. So now I can look at the unit circle, but I can put radians on there. So now we see that, well, 30 degrees is really pi over 6, and the cosine value is square root of 3 over 2, 1/2. So the cosine of pi over 6 is square root of 3 over 2, 1/2. So take a minute to familiarize yourself with this unit circle. It comes in very handy knowing both the degrees, the radians, and your cosine and your sine values. Special thanks to our sponsors for helping create these videos.